Antiderivatives are not unique, right? We know that if f is a function and big F is an antiderivative, then we can enumerate all antiderivatives by looking at big F of x plus c as we let c range over the real numbers. But if we give one more piece of information, say like the value of the function at a point, then we should be able to find a unique antiderivative big F. To show you what I mean, let's do an example. Let's find the antiderivative of the function little f of x equals 3 over x cubed, which satisfies big F of 1 equals 6. So first, let's find the general antiderivative. Writing 3 over x cubed as 3x to the negative 3, the general antiderivative is of the following form. Here, I'll include the plus c immediately because we're working with general antiderivatives. So there's nothing new going on here. We've done our usual process of finding the antiderivative. On the other hand, we've yet to apply the extra piece of information that we know, namely that f of 1 is equal to 6. So let's plug 1 into our equation above, set it equal to 6, and use this to solve for c. Doing so gives a value of 15/2. So if we take this value for c and plug it back into f, we get our final answer as so. Now including that plus c term immediately helps us to remember that it's there. Let me show you why it's important using a different kind of example. Let's suppose this time that we're given a function and told that it's twice differentiable and that f double prime is square root x. If f of 0 is 2 and f of 1 is 3, what's f? So while not set up as our standard antiderivative problem, this is an antiderivative problem. And the key lies in recognizing that f prime is an antiderivative of f double prime. This is because differentiating f prime gives us f double prime. Proceeding as usual and writing f double prime of x is x to the 1/2, we get that f prime of x looks like this. And with some simplification, we get the following. Now, in the same manner as above, f is an antiderivative of f prime. So we take another antiderivative to get our general form for f. Notice that because c is a constant, that when we take an antiderivative, it picks up this factor of x. If we had waited until the very end to add the constant, then we might have missed this fact. Anyway, simplifying a bit more to make the function look nice gives us this. Now we can start applying the conditions that we were given. Note that we have two conditions, and we have two constants. And that's going to be true in general. You need a condition for each constant which appears. I'm going to start with the condition that f of 0 is equal to 2, just because plugging in 0 results in a lot of cancellation. From this, we can just read off that d is equal to 2. Putting that back into our function, f now looks like this. To take care of that c, we need to use the second condition that f of 1 is equal to 3. Plugging that in and solving it for c gives us that c is equal to 11/15. We thus have all the constants, so our function f is no longer a generic antiderivative, but instead looks like this. So a few quick notes. It's possible in a question like this that one of our conditions is on f prime. So for example, f of 0 could be 2, and f prime of 0 could be 3. It's also possible that when you substitute the conditions, you get a system of equations whose variables are your constants. You would then need to solve this system in order to find your constants. So give it a shot. Try changing the given conditions around and see how that changes your answer.